Experts predict that in the next 10 years, 500,000 people will die on highways in the United States alone. The losses due to death, injury, and property damage will exceed $1 trillion. Don't you wish there was a systematic way to identify and solve highway safety problems? Well, there is. It's called Highway Safety Improvement Program Management. This management system is covered in 3 IRF videotape programs. This one, plus evaluating and selecting the best safety alternatives, and evaluating safety program results. This is Bill Grenke. He is a safety engineer with the State Highway Department. He is just now reading about a Highway Safety Improvement Program management system. According to the National Cooperative Highway Research Program report he is studying, this system will identify real problems instead of perceptions. The solutions will be cost-effective, and in the event of legal actions, the existence of the system will aid the defense. Naturally, Bill is a bit skeptical. He has dealt with highway safety for years. He knows motor vehicle movements involve a complex set of interrelationships between drivers, vehicles, and the roadway. Many situations, including fatigue, bald tires, potholes, and blowing dust, can affect the driver's ability to respond to an emergency situation. Combining these variables with high traffic volume increases the complexity. When one or more of these situations arise, accidents may occur. Sorting out what causes the accidents and what can be done to prevent them in the future is the challenge of highway safety professionals. Bill is used to considering improvements that affect the stages of an accident: pre-crash, crash, and post-crash. Pre-crash improvements aim at reducing the frequency of accidents. Crash and post-crash improvements aim at reducing the severity of accidents. These improvements involve the roadway, the vehicle, and the driver. The systematic approach Bill is reading about addresses the roadway category. Highway Safety Improvement Program Management has 6 phases. They are: Phase 1, identify safety problems. Phase 2, identify alternative improvements. Phase 3, evaluate alternatives and select improvements. Phase 4, develop and implement the Highway Safety Improvement Program. Phase 5, evaluate each safety improvement. And Phase 6, evaluate overall safety program. There are 4 steps involved in Phase 1. Identify safety problems. Step 1 is to identify hazardous locations. A location is either a spot along the road or an intersection. There are 2 ways Bill can make his determination. He can use accident data analysis, which requires at least 1 year of historical data on highway accidents. Using computer records and analysis programs, he can compare accident location information. Or he can use conflict analysis. That requires visual identification of areas with indications of hazardous conditions, such as frequent skid marks. It may also mean doing intersection turning analysis. These methods, of course, are not as accurate as accident data analysis. Bill may have to use them when accurate historical accident data is not available. The next step in identifying safety problems is analyzing and ranking the locations. There are several possible methods he can use. One is the number method, which means he must plot a year's worth of accidents on a road map. Then he can easily identify locations with the largest cluster of accidents. This method is good in small jurisdictions with low numbers of accidents. The number method does not consider accident rates, so there is also the rate method. If Bill identifies different locations with the same number of accidents, but one has substantially more traffic than the other, then he needs to show that the location with less traffic is more hazardous. Using the rate method, he can prove it. He divides the number of accidents at a location by the number of vehicles approaching the location in millions, giving a rate of occurrence expressed as annual accidents per million vehicles. R is the accident rate at the spot or intersection in annual accidents per million vehicles. A is the number of accidents during the time period. T is the time period, usually 365 days. And V is the traffic volume approaching the spot or intersection in vehicles per day. Another method Bill can use is the rate quality control method. Research has shown that accident occurrence follows a statistical pattern known as the Poisson distribution. Using another formula, Bill can identify locations with a critical accident rate, an accident rate that is above normal. In this formula, R sub C is the critical accident rate in annual accidents per million vehicles. R sub A is the system-wide average accident rate for a specific type of road in annual accidents per million vehicles. M is the vehicle exposure in millions of vehicles per year. And K is the constant that establishes the level of confidence. Then, by subtracting the critical rate, R sub C, from the actual rate, R, he will come up with a quality control number, Q sub C. The computer can sort these rates in descending order. That will give Bill a list of hazardous locations ranked from the very worst to the least worst conditions. Step 3 of identifying safety problems is to compare the high accident location list with the current capital improvement program. If a hazardous location is already scheduled for improvement, Bill can take it off his location list. If a hazardous location has had recent improvements but is still a problem, Bill will leave it on the high accident list for more improvements. To finish out this phase of the program, Bill will prepare a report. It will list all the high accident locations from the most important on down, based on the quality control numbers. He will use this report in the next phase of analysis to determine the most appropriate improvement for each location. Let's look at that phase. In this phase, Bill will identify alternative improvements. There are 4 steps. Step 1 is to obtain accident data. Police file accident reports on most accidents. They should make them available to traffic engineers responsible for conducting safety studies. If report forms are designed and filled out properly, they will have the best information on the types and causes of accidents at specific locations. His next step is to analyze the accident data. As he categorizes the accidents, he'll discover patterns that will help him determine the causes of accidents at that location. There are forms available that break accidents into groups. Now it's time for Bill to do a field investigation. He will look for one or more improvements that could be made to each location. He should ask himself, are there blind corners? Are signs and signals easy to understand? Is the channelization clear? What about parked cars and advanced warning signs? There are worksheets available to help with this effort. Bill is an experienced traffic engineer, so he will probably come up with at least one improvement for each location. As he prepares to make recommendations, he must remember there are 4 increasingly complex ways of dealing with a hazardous location. The first is to do nothing. This is usually not acceptable, but must be considered as an alternative nonetheless. The second alternative is to modify the location. That could mean replacing rigid signs with breakaway ones, or putting in a median barrier. The third alternative is to change the flow of traffic. That could mean reducing the speed limit, putting in turn signals, improving signs, or adding pavement markings. The fourth alternative is to eliminate the hazard altogether. This is usually done through construction of a grade separation or some other major improvement project. Now Bill is ready for the fourth and final step in this phase, a report on his findings. For each location, he should indicate the types of accidents, their probable causes, and the alternative improvements to the location. Through a logical and systematic process, our friend Bill is finding out that he can identify a series of alternatives. In this program, we followed traffic engineer Bill Grenke as he learned about a systematic approach to highway safety improvement program management. It has 6 phases. They are: Phase 1, identify safety problems. Phase 2, identify alternative improvements. Phase 3, evaluate alternatives and select improvements. Phase 4, develop and implement the Highway Safety Improvement Program. Phase 5, evaluate each safety improvement. And Phase 6, evaluate overall safety program. Phase 1 involves identifying hazardous locations. There are 2 ways Bill can make his determination. He can use accident data analysis, or he can use conflict analysis. That requires visual identification of areas with indications of hazardous conditions, such as frequent skid marks. The next step in identifying safety problems is analyzing and ranking the locations. There are several possible methods he can use. One is the number method, which means he must plot a year's worth of accidents on a road map. The number method does not consider accident rates, so there is also the rate method. Another method Bill can use is the rate quality control method. Research has shown that accident occurrence follows a statistical pattern known as the Poisson distribution. Step 3 of identifying safety problems is to compare the high accident location list with the current capital improvement program. If a hazardous location is already scheduled for improvement, Bill can take it off his location list. If a hazardous location has had recent improvements but is still a problem, Bill will leave it on the high accident list for more improvements. To finish out this phase of the program, Bill will prepare a report. It will list all the high accident locations from the most important on down, based on the quality control numbers. Phase 2 is developing alternative improvements. Step 1 is to obtain accident data. Police file accident reports on most accidents. They should make them available to traffic engineers responsible for conducting safety studies. If report forms are designed and filled out properly, they will have the best information on the types and causes of accidents at specific locations. His next step is to analyze the accident data. As he categorizes the accidents, he'll discover patterns that will help him determine the causes of accidents at that location. Now it's time for Bill to do a field investigation. He will look for one or more improvements that could be made to each location. He should ask himself, are there blind corners? Are signs and signals easy to understand? Is the channelization clear? What about parked cars and advanced warning signs? As he prepares to make recommendations, he must remember there are 4 increasingly complex ways of dealing with a hazardous location. The first is to do nothing. The second alternative is to modify the location. The third alternative is to change the flow of traffic. The fourth alternative is to eliminate the hazard altogether. Now Bill is ready for the fourth and final step in this phase, a report on his findings. For each location, he should indicate the types of accidents, their probable causes, and the alternative improvements to the location. Through a logical and systematic process, our friend Bill is finding out that he can identify a series of alternatives. Picking the best alternative for each location is the purpose of the next phase. That phase and the ones following it are covered in 2 more IRF videotapes in this series. For more information on this or other IRF videotapes, write to the International Road Federation or call the numbers on your screen. This is Bill Grenke. He is a safety engineer with the State Highway Department. He has been reading about a Highway Safety Improvement Program management system. According to the National Cooperative Highway Research Program report he is studying, this system will identify real problems instead of perceptions. The solutions will be cost-effective. And in the event of legal action, the existence of the system will aid the defense. The system has 6 phases. Phase 1, identify safety problems. Phase 2, identify alternative improvements. Phase 3, evaluate alternatives and select improvements. Phase 4, develop and implement the Highway Safety Improvement Program. Phase 5, evaluate each safety improvement and Phase 6, evaluate overall safety program. In the previous program of this series, Identifying Highway Safety Problems and Solutions, we followed Bill as he learned about the system's first two phases. In this program, Bill will work his way through the third phase, evaluating alternatives and selecting improvements, and the fourth phase, developing and implementing the program. For the third phase, he will find the best alternative improvement through an economic analysis. The best improvement is the one returning the greatest net benefit in terms of the cost of the improvement, as well as reduced costs to society by preventing accidents. His first step is to look at the alternative improvements for each high accident location. Then, he must estimate the reduction in number and severity of accidents for each alternative. His agency may have results of previous similar improvements. If not, there are international research results. These forecast documents provide information like percent reduction expected and service life of an improvement. Now, starting with the first location, Bill has to calculate the expected accident reduction for each alternative. He should use this formula. The accident reduction, A sub R, is in terms of accidents per year. It is calculated by using the annual accident rate, or R, in accidents per million vehicles per year approaching the spot or intersection, or little m, and the expected percent reduction in accidents for the type of proposed improvement, or P sub R. Next, Bill will calculate the safety benefits to society for each alternative. He will figure this value by multiplying the number of accidents prevented by the total cost of each accident to society. The cost of an accident will vary depending on the country and jurisdiction. In the United States, the Urban Institute estimated societal costs in 1988. The costs associated with motor vehicle accidents and injuries were $4,490 for property damage, $69,590 for non-fatal injury, and $2,722,550 for fatal injury. Now, based on the average distributions of types of accidents, Bill can determine the average cost per accident. In 1988, one state estimated that the average cost per accident was $51,770. By using a consumer price index, Bill can calculate current year costs. Here's the formula. C sub A is the current year cost per accident. C sub X is the cost of accidents in previous year X. R is the annual rate of growth in accident costs in percent. And N is the number of years of growth. In other words, the difference between current year and previous cost year. This procedure works for any country with accident cost figures. If data is not available, engineers can convert USA figures using a relative cost of living index. Then update the costs to current year figures using a local consumer price index. That should only be an interim measure until there is more precise local data. Now, Bill can estimate the first year benefit from each improvement. B is the first year safety benefit from the accidents prevented in monetary units. A sub P is the annual reduction in number of accidents. and C sub A is the current year cost of an accident in monetary units. There is still one last calculation. It adjusts first-year safety benefits to allow for future increases in traffic growth. It also converts benefits to equivalent uniform annual benefits so they are comparable to improvement costs. EUAB is the equivalent uniform annual benefit in monetary units. B is the total first-year safety benefit in monetary units. And EUS is the equivalent uniform series factor based on the traffic growth rate and the money interest rate for the number of years of service life of the safety improvement. As an example of the size of the EUS factor, if the traffic growth rate is 2% per year, the interest rate is 6% per year, and the service life of the improvement is 15 years, the EUS factor is 1.151. Next, Bill has to calculate the improvement costs. Initial capital investment or implementation costs are usually the largest. They may be design and construction costs for large improvements like a grade separation interchange structure, or simply labor and equipment costs for maintenance forces doing removal of a roadside obstacle. Initial investment costs can be estimated from the cost of similar projects in past years. If the previous costs are more than 1 year old, they should be adjusted to the current year using a suitable price index. The formula for updating costs has C sub I as the cost of investment in current year monetary units, C sub IX as the cost of investment in previous year X, P sub I as the price index for the current year, and P sub IX as the price index for previous year X. After determining the initial investment cost, Bill must convert that to an equivalent uniform annual cost. This formula places initial costs on the same annual cost basis as all other costs and benefits. In this equation, EUAC sub I is the initial investment cost expressed as an equivalent uniform annual cost. C sub I is the initial investment cost in current monetary units. And CRF is the capital recovery factor for a given interest rate and service life. There is still the annual maintenance and operating cost of the improvement. Bill must figure that as well. Routine maintenance costs include items such as damage repair, sign cleaning, and signal light replacements. Operating costs include items such as energy consumption for traffic signals or street lights. Bill can get cost estimates for these items from the maintenance or operations manager. He simply adds the annual cost of operation of the improvement to the annual cost of maintenance of the improvement. Finally, Bill must find out if the improvement may have some terminal or salvage value at the end of its service life. For example, rusted or damaged guardrail may have some value as scrap metal. If the salvage value is small compared to initial capital cost, say 1 to 2%, Bill should ignore it. If not, he should estimate the value of the salvage for the terminal year and convert it to an equivalent uniform annual cost using a sinking fund factor. Here is the formula. EUAC sub S is the salvage value in equivalent uniform annual cost. C sub S is the salvage value at the end of the service life. and SFF is the sinking fund factor for a given interest rate and service life. Now, Bill can figure the total equivalent uniform annual cost of each improvement. He does it by combining the initial cost, the operating and maintenance costs, and the salvage value. Some improvements will have an abbreviated service life. For example, the service life of an improvement may be 10 years. But if a major road reconstruction project is scheduled on the same road in 5 years, the improvement will really only have a service life of the 5 years. When he has computed the total cost of improvement for each alternative, Bill is ready to evaluate the alternatives. To do that, he must figure out the net annual benefit. The greater the net annual benefit, the more desirable the improvement. If the NAB is positive, then society will experience a monetary net benefit as a result of making the improvement. If the NAB is 0 or negative, then the money would be better spent on a different type of improvement or on a different location. Another useful measure is the benefit-cost ratio, B over C. When the B over C ratio is greater than 1, the project is desirable. The larger the B over C ratio, the more desirable the project. Bill's last step in this phase is to rank the alternative improvements. There are convenient worksheets for recording the economic analysis for each alternative at each location. These worksheets should be included in a safety project planning report for each location. Normally, Bill would recommend the most cost-effective improvement. If funding is limited, however, he might hold off on something like a major grade separation interchange and pick a lower-priced improvement. Now it is time for Bill to learn about Phase 4, developing and implementing a safety program. It will not be easy. The program must have quick, efficient, and orderly improvements, and they must be within the limits of available funds and other resource constraints. The first step is development. A safety improvement program is a bit unique. Projects are wide-ranging, from minor improvements such as signs and pavement markings to major at-grade intersection reconstruction or grade separation interchange construction. So dealing with them is a bit different. Some work may be done by in-house forces and some by private contractor. Engineers often like to concentrate on large, glamorous projects and ignore small but urgently needed ones. Creating a separate safety improvement program may ensure that small but urgent projects get appropriate attention. Some countries have dedicated funds for safety improvements. That means developing a separate program to utilize funds properly. In any case, development is basically applying available funds to proposed projects in priority order. If the cost for all improvements is high, it may require a multiple-year program. The next step is implementation. The agency will handle large safety projects the same as regular capital improvement projects. They will involve design and either in-house or contract construction forces. Traffic or maintenance forces may perform smaller projects with a minimum of design work. The key to success is to make sure procedures and responsibilities are well defined and carried out. Managers must understand safety improvements are generally low-cost, quick projects with highly effective results. Also, a traffic engineer should be on site for small jobs done by in-house forces without construction plans. There may be questions about such things as size, type, and location of signs and signals, or proper placement of pavement markings, guardrail, and other safety devices. The engineer can make sure improvements conform to acceptable standards and address the safety need at the location. A last, very important step is documentation of the as-built improvement. There are two important dates to document as well: the date of the last day the unimproved condition existed, and the date that traffic began operating under the improved condition. Safety analysts need this information to compare accident experience before and after the improvement and determine the extent of the improvement's success. In this program, Bill Grenke has worked his way through the third and fourth phases of the Highway Safety Improvement Program process, evaluating alternatives and selecting improvements, and developing and implementing the program. In the next program of this series, Evaluating Safety Program Results, we will cover the final two phases. For more information on this or other IRF videotapes, write to the International Road Federation or call the numbers on your screen. This is Bill Grenke. He is a safety engineer with the State Highway Department. He has been reading about a Highway Safety Improvement Program management system. According to the National Cooperative Highway Research Program report he is studying, this system will identify real problems instead of perceptions. The solutions will be cost-effective, and in the event of legal action, the existence of the system will aid the defense. In the previous programs of this series, we followed Bill as he learned about the system's first four phases. They are Phase 1, identifying safety problems; Phase 2, identifying alternative improvements; Phase 3, evaluating alternatives and selecting improvements; and Phase 4, developing and implementing the Highway Safety Improvement Program. In this program, Bill will work his way through the last two phases, evaluating each safety improvement project and evaluating the overall safety program. The first step in evaluating a safety project is to obtain before and after accident data. Before means before any construction, and after means only after the construction is complete. Bill will find out that in gathering information, he must consider the sphere of influence. Improvements like a curve warning sign or reduced speed sign can influence accident experience well beyond the physical location of the improvement. On the other hand, an improvement such as realignment of a curve or a new guardrail generally affects accident occurrence only within the physical limits of the improvement. Improvements at intersections are generally more difficult to evaluate. An intersection improvement may affect accident occurrence over 1 block away. However, as the distance from the intersection improvement increases, the possibility of other influences also increases. Also, Bill should exclude non-intersection related accidents altogether, like collisions with cars emerging from parking spaces or mid-block pedestrian accidents. There is still one other complicating factor for Bill to think about. The total number of accidents may not drop. It may even increase. But accident severity may drop enough to easily justify the improvement. For example, after adding a median barrier, more vehicles might collide with the barrier. However, fatal and injury accidents might drop because vehicles no longer cross over the median and have head-on collisions. In cases like this, safety benefits based on accident severity determine whether or not the barrier was cost-effective. So before and after accident data must include the severity of accidents as well as total numbers of accidents. Bill will also have to get before and after traffic data for each improvement area. If it is not available, he can estimate it using these formulas. V sub B is the estimated traffic volume for the year prior to improvement in vehicles per day. V sub A is the estimated traffic volume for the year after improvement, also in vehicles per day. V sub X is traffic volume for year X based on counts and adjusted to get average annual daily traffic in vehicles per day. R is the annual growth rate in percent for traffic on the road being studied. It may be positive, 0, or negative. And N is the number of years from year X to the analysis year. The next step is to analyze the accident data and adjust it for overall traffic growth. Here is the formula that will work for both before and after data. AA sub B is the adjusted annual number of accidents before improvement in number of accidents. A sub B is the annual number of accidents before the improvement in number of accidents. V sub B is the estimated traffic volume for the year prior to improvement in vehicles per day. And V sub A is the estimated traffic volume for the year after improvement in vehicles per day. AA sub B is the number of accidents that would have been observed in the period after the improvement if the improvement had not been made. Now, the before and after accident data can be evaluated strictly on the basis of the influence of the improvement. Now Bill can calculate the percent reduction in accidents due to the improvement. PC is the percent change in number of accidents due to improvement. AA sub B is the adjusted annual number of accidents before improvement in number of accidents. And A sub A is the annual number of accidents after improvement in number of accidents. When the percent change is negative, the total number of accidents following the safety improvement has dropped. A positive number means it increased. He can use the same formula for the adjusted annual number of fatal, injury, or property damage accidents before the safety improvement. Bill now knows how to figure the percent of change in number of accidents at a location. But how significant is the change? Is it only chance? He can find out with another simple equation. It is based on the theory of Poisson distribution. PC sub C is the critical percent change in number of accidents. AA sub B is the adjusted annual number of accidents before improvement in number of accidents. K is the standard normal variable on the x-axis of the standard normal distribution curve. Let's look at K more closely. K is related to the probability, P, that the critical percent change, PC sub C, will not be exceeded due to chance. A 95% confidence level, or K equals 1.645, is recommended for most evaluations. For small numbers of accidents, say less than 20, a higher confidence level may be warranted. This job is easier with a standard chart. All Bill has to do is plot the point represented by the adjusted annual number of accidents before improvement, AA sub B, and the actual percent change in number of accidents, PC. In this case, the point fell below the lower curve, so the change is significant at the specified confidence level, and the safety improvement has been a success. If PC had fallen between the two curves, that would mean the change was probably due to chance and not to the safety improvement. If it had fallen above the upper curve, the situation was probably made worse by the safety improvement. The significance test is good for fatal, injury, and property damage accidents as well. The next question Bill has to ask is, was the improvement worth doing from an economic viewpoint, or should the agency have spent the money on some other safety improvement? He can answer that question by calculating the average annual economic loss at the location before and after the safety improvement. There is a formula for each. EL sub B is the annual economic loss before the improvement in monetary units. EL sub A is the annual economic loss after the improvement in monetary units. AA sub B is the adjusted annual number of accidents before. A sub A is the annual number of accidents after. C is the societal cost of each accident. F is the subscript indicating fatal accidents. I is the subscript indicating injury accidents. And P is the subscript indicating property damage accidents. He can also calculate the equivalent uniform annual benefit, EUAB. He can also calculate the net annual benefit, NAB, and the benefit cost ratio, B over C. The greater the net annual benefit, the more desirable the improvement. A positive NAB means society will experience a monetary net benefit from the improvement. If the NAB is 0 or negative, then the money would be better spent on a different type of improvement or location. The benefit cost ratio is an indicator of the cost effectiveness of the project. The benefit is related to the reduction in accidents. A ratio greater than 1.0 indicates the project was cost effective. On projects involving small numbers of accidents, the ratio may be very large, but the net annual benefit value may be relatively small. The benefit-cost ratio is a better indicator of the effectiveness of various types of improvements, while the net annual benefit value is more useful for evaluating the overall benefit of the safety program. Bill should record the NAB and B over C values for each safety project, even if they indicate the project was not successful. Safety analysts will use these records to learn how different types of improvements perform. Now Bill is ready for the last phase, Phase 6, evaluating the safety program. The first step is to evaluate categories of improvements. Classification codes can make this job easier. For example, channelization of turning lanes is code 10, and sight distance improvement is 13. When the improvements are all in categories, Bill must aggregate the annual accident data, benefits, and costs. For example, he should treat all pavement marking projects as one category. However, if a project involves a combination of pavement marking and signing, he should not combine it with the pavement marking only projects. He should create a separate category indicating the specific combination of improvements. Also, he should not combine projects at highly dissimilar locations. In other words, signing and marking projects at railroad crossings should be separated from signing projects at other locations. Now, for each project in each category, Bill must calculate the overall percent change in accidents, total benefits, total costs, total net benefits, and overall benefit-cost ratio. Here are the formulas. PC sub O is the overall average percent change in number of accidents for all projects in the improvement category. Sum AA sub B is the summation of the adjusted annual number of accidents before improvements for all projects in the improvement category. Sum A sub A is the summation of the annual number of accidents after improvement for all projects in the improvement category. EUAB sub O is the overall equivalent uniform annual benefit for the improvement category. EUAC sub O is the overall equivalent uniform annual cost for the improvement category. Sum EUAB is the summation of equivalent uniform annual benefits for all projects in the improvement category. And sum EUAC is the summation of equivalent uniform annual costs for all projects in the improvement category. Now, Bill can calculate the overall performance of a specific category of improvements. The overall net annual benefit, NAB sub O, and the overall benefit-cost ratio, B over C sub O, for all projects. The greater the net annual benefit, the more desirable the improvement category. A positive NAB sub O means society will generally experience a monetary net benefit from this type of improvement. If the NAB sub O is 0 or negative, then money would be better spent on a different type of improvement. The overall B over C sub O ratio is an indicator of the cost effectiveness of the improvement category because the benefit is related to the reduction in accidents. A B over C sub O ratio greater than 1.0 indicates this category of improvement is cost effective. Once he has summaries for each category, Bill can aggregate them to obtain the combined overall result of all projects in the safety program each year. There are forms for this also. In future years, he can combine annual worksheets. Over a period of years, the agency will develop valuable data on most safety improvement categories. The agency must be sure to update costs and benefits from previous years with appropriate inflation factors. This entire process is complete when Bill writes an annual evaluation report on the traffic safety program. The report should describe program activities during the year and summarize the results of program evaluations. It should include worksheets with categories for the year and with cumulative totals for the last 5 years. The report should highlight the overall accident reduction and the net annual benefits of the program, or suggest actions to improve performance in the future. And perhaps most important, this report should circulate to safety program managers and top management. It will help to focus attention on traffic safety program management in the future. In this program and the previous 2 of the series, traffic engineer Bill Grenke has worked his way through the 6 phases of the Highway Safety Improvement Program process. For more information on this or other IRF videotapes, write to the International Road Federation or call the numbers on your screen.